It's indeed an honor and privilege to be here for these celebrations. But because we are celebrating something which is 60 years old, it's perhaps not a bad idea to take another look at it in a slightly different way. So my talk wouldn't be anything qualitatively new, but I shall be looking at things that we know, perhaps in a slightly different way. The first thing I do talk about is the distinction between global and gauge invariance. I mean, global symmetry and gauge invariance, and I prefer not to use the word symmetry in context with gauge. And the reason is, we all know from our studies in quantum field theory or in classical field theory that when you have a continuous global symmetry, you have a conserved current. And corresponding to the conserved current is a Noether charge, which generates transformations, infinitesimal transformations on the fields, on the physical degrees of freedom. On the other hand, when we have a gauge, when we gauge a global symmetry, we actually have no new conservation laws. And in fact, the gauge, the symmetry charges, the Noether charges, now become first-class constraints. Now, this was actually already mentioned in one of the earlier talks. I'm just emphasizing this because I think this could be important. You see, gauge transformations, basically, if you apply gauge transformations on gauge potentials, they only happen to change inhomogeneously a part of the gauge potential, which is a pure gauge. And it leaves the physical part of the gauge potential unaffected. That's what you mean by a gauge transformation. And therefore, you might wonder if you could formulate gauge field theories without these unphysical degrees of freedom. Now, what I'm going to talk about are certain very preliminary observations on physical on-shell polarizations of linear gauge fields, of Abelian massless linear gauge fields. And then I shall go, then I shall go on to the Higgs phenomenon in the classical Abelian Higgs model. Now, this is something that most of you probably have seen, but once again, perhaps the only novelty here would be not to mention or not even to allude to the Nambu-Goldstone phenomena or the appearance of Goldstone modes. We shall try to extend that to the gauge Higgs sector of the electroweak theory, the classical level. And then, because I'm always allergic to the particular form of the Higgs potential in the standard model, which is put in by hand, I'd like to generate it by one-loop corrections via the Coleman-Weinberg Higgs mechanism. And we'll see what precisely is the symmetry that is broken by these quantum corrections. It's certainly not electroweak's gauge invariance. So first of all, I begin with the work of Singh many years ago, where he classified all spherically symmetric spacetimes, curved ones of course included. All spherically symmetric spacetimes could be thought of as the Cartesian product of a Lorentzian two-plane or a two-fold and a two-sphere, an ordinary two-sphere. For instance, if you talk about Minkowski spacetime, this is quite obvious. In Minkowski spacetime, if you use light cone coordinates, u and v, then you can see that this is the part which is relevant for the I11, the Lorentzian two-plane. And this is the metric on the sphere, as we know, with a radius which is dictated by where on the two-plane the sphere is located. So this is well known. Now, I'm not going to use this coordinate basis right away, but remember certain very elementary things from electrodynamics, Maxwell's equations. So I've gone to Fourier space where this looks like this. And now, if this L square here is not zero, then of course the only solution I have is a pure gauge. On the other hand, if L square is zero, then of course the component of A along the direction of L will have to be zero. So that's automatically a gauge condition for you, if you wish. It's not really a gauge condition because I have not chosen it. It's simply a consequence of the choice L squared equal to zero. Now, what I'm going to now discuss is introduce, well, this is probably too much, but I can I'm going to introduce these null vectors. So I have the L as a null vector. In addition, I shall have N, M, and M bar, these being complex conjugates of each other. These are all null vectors, and we are going to work in Minkowski space, but these are the inner product rules that I'm going to assign them. Now, immediately, what transpires is that FAB is actually independent of AN, which means that AN must be a pure gauge. So we have AL equal to 0, and then AN is a pure gauge. So for free Maxwell field, then, we are left with two physical degrees of freedom. And these are the on-shell connection components, and you can see that these are the components that must live on the sphere. So this is our conclusion. If you wish to use local coordinates on the sphere, then you could write these 4 vector M's in terms of theta. These are functions of theta and phi on the sphere. So they have 2 directions, theta and phi, on the sphere. In other words, if you have massless gauge fields, then their physical polarizations must lie on the sphere. Now, you could play the same game with gravity, with linearized gravity, and because the time isn't too long, I must just show you the results. Once again, you have LAHAB equal to 0 and NAHAB equal to 0. So that automatically reduces the number of components to 2, basically. You also have a relationship between HMM and HM bar M bar. So you have 2 independent degrees of freedom, both of which live on the S2. So this is rather nice, I think, because we are now thinking of calculating graviton amplitudes, and this could play a role there. So the proposal, in fact, is this is really a proposal, that all massless gauge fields of any rank whatsoever actually live, the physical polarizations actually live on the S2. The proof is under construction, but I think you can guess that something like this would play a role. So you construct, if it's a rank R field, then you would simply get the S projection by taking these projection operators, where this is this projection operator right here. So you construct this whole string of projection operators, excuse me. If there is any residual gauge invariance on S2, that could be removed by a further projection like this. Of course, this is just my guess of a proof. I still haven't gotten there. And I would like to, of course, associate these 2 physical projections with the 2 helicity states of one particle, 2 helicity components of the one particle state. That is already known from the representation theory of these fields. Now, of course, we would like to go beyond free fields and try to compute S matrices, and it's useful to say that this kind of a parametrization might be useful for computing S matrices. Now, if you go off-shell, then there's a unique projection which gives you, on the electromagnetic vector potential, which gives you something like this, which is a purely transverse, space-time transverse object, which is gauge invariant, which has 0, 4 divergence, and of course, which satisfies this equation, which is now what the Maxwell equation reduces to. And this simply tells you that you can decompose A like so, where this fellow AL, the longitudinal part, is a pure gauge. This is again known, but this is just to emphasize that all the physical degrees of freedom, the curvature, the holonomies, are actually functions of only the physical part of the vector potential. So there's a physical part of the vector potential, and I'm trying to make sure that that's what we play with. So basically, the idea is, from now on, we shall not really talk about AL, because nature doesn't admit AL. It's an artifact. So now on to the Abelian Higgs model. That's the Abelian Higgs model. This is the U1 covariant derivative, the gauge covariant derivative. You make a polar decomposition like this, and this is the action that you get. Now this action, this is all very simple stuff. You know what the gauge transformations are, it's completely gauge invariant. But you can now introduce what I call gauge-free variables, AT, like we did earlier, and the theta, capital theta being small theta plus AL. If you do that, then it's obvious that these will not transform under gauge transformations. and you have a gauge-free action where every degree of freedom here is physical. Now you can actually eliminate, so look, I have not talked about any spontaneous symmetry breaking. I have not alluded to any mass generation yet. Even before mass generation, you could actually eliminate, the theta degree of freedom, because the only place it occurs, excuse me, is here. There's nowhere else is the theta degree of freedom, and therefore you could simply eliminate this by defining a new A field, which will be this. But remember though, that while AT is transverse, it has 0 divergence. If you take this combination, it will not be. Wow. Really running, okay. And then the mass generation, again, has nothing to do with spontaneous symmetry breaking of any symmetry. All you have to assume that this is true, and these are the masses. So there's no violation of gauge invariance, okay? Anyway, since I'm running short of time, I shall not have much time to give you the SU2 version. I shall simply flash the transparency. So what you do is that this is the SU2 doublet, Higgs doublet. This is the Higgs gauge field sector. Excuse me. This is the Lagrangian. And these are defined, I think, in the next transparency. But the important thing here is to make this decomposition, where you introduce this matrix G, which is parametrized in terms of the chi matrix, which carries all the gauge transmission properties. And now you can show that G has these transmission properties. So if you now define a new set of variables, like so, the W variables, like so, the W gauge bosons are redefined as compared to the previous gauge bosons, then you can see that the W is now gauge invariant under SU2 gauge transmissions. It, of course, has a U1 gauge transmission because it's still charged. And then we can define these physical boson fields like so, and with the physical charges related to the electronic charge. This is all very well known, but the point is that you still have a U1 gauge invariance left over. But because we've already dealt with the U1 gauge invariance, it's not a problem at all. You can eliminate the residual U1, just like I did earlier. And now we have this equation. Okay, so I think I have the, these are the new terms, and you can see that this is how the photon appears. So this is the photon which appears with a longitudinal degree of freedom. However, there is nothing which can give the photon a mass. So all this simply goes to give you the right answer. You again, here of course, since you don't have a Higgs potential, you can't give mass to anything, but for that, I shall skip this novel interpretation. All you have to do is do one-loop quantum corrections a la Colvin and Weinberg. So I don't put in a Higgs potential. I'll skip this. So one-loop quantum corrections give you this. And well, again, let me not allude to the subtle new novel interpretation. I'll just get here because I'm running out of time. And do I have a minute or 2 minutes? Okay, great. So this is the effective one-loop potential. M here, this is the renormalized effective potential, so M here is a renormalized mass. Everything has been renormalized, renormalization mass scale, I'm sorry. Now what we notice here is that everything just depends on the gauge coupling, as you'd expected, but you do have enough structure here now to go through the Higgs phenomenon. So that's been done, and what you see is that you can find a rho zero from here. That's a little complicated formula which I haven't bothered to write down. But there's a rho zero, and you can compute the masses in terms of rho zero exactly the same way as before. However, if you now wish to compute the Higgs mass from the second derivative of the potential, the effective potential at its minimum, then you find 10 GeV, provided, of course, you choose the renormalization scale to be MZ, and that's a phenomenological disaster. So my great dream has fallen flat, didn't work, but Antiniemi was here a couple of days ago, and he said, perhaps the mistake is you didn't include this term. And if you did include this term and made some assumptions about what lambda was in terms of the gauge couplings, then you could probably have a higher mass. Now that's an exercise which I'll have to do. Do I have like half a minute? I think this is my second last transparency. Now I wanted to do the same thing for a pure Yang-Mills theory without any Higgs. The idea is that you first introduce these Wilson lines or holonomies and you look at their gauge transmissions. Of course, Wilson lines depend on 2 points, but if you take one of those points to infinity, where the gauge transmission becomes unity, then this is how the Wilson line would transform under a gauge transmission. And now you can define this because from infinity to the point, to the field point are a number of curves, infinite number of curves. So if you averaged over all those curves, you can define this like this, define a new variable A, new variable A, whatever, the script A or whatever, like this. And if you did make a gauge transmission, then this is gauge invariant. Okay, this is not completely local, but it's local in the sense that after integration, it's of course dependent on only one space-time point. But this is perhaps one way of introducing a completely gauge-free Yang-Mills potential. I don't know if you can realize this as a, so this is my last slide. These are some outlook points. Obviously, the aim would be to calculate S matrices for linear gauge fields like gravitons. Now, what does this scale symmetry breaking mean? I forgot to emphasize that the only symmetry that you actually broke through the Higgs mechanism, and you could say that dynamically, of course, is scale symmetry. So there's a scale anomaly that has appeared because of radiative corrections. There's no other symmetry breaking. SU2 cross C1 gauge invariance is absolutely intact. I don't know if the gauge-free formulation helps in computing non-perturbative correlators, but of course, we expect in Yang-Mills theory, as it had a very glorious past, to have an equally bright future. Thank you very much.
I have one question to you. You made this observation that if you have a global symmetry of conserved charge, if you gauge it, make it local, you get nothing new. Why is that?
Well, because when you gauge it, basically there are many ways to answer this question, but the simplest way perhaps is that you're introducing a new field into the game, which is unphysical, because you'd introduced it. And nothing should depend on that field. No. So the conserved quantity that you had becomes a constraint. No, it becomes a first-class constraint. Yes. And that's true for all gauge fields, including gravity, of course. Thank you.